Okay. Okay. So like DevDay is a monthly event that we conduct with our community, so that we give talks, present talks, so that community can benefit from the knowledge sharing. This is like a monthly event that happens across Pune, Bangalore, and Chennai. Yeah, this is one of the talk in that series itself. So today we are going to talk about JVM GC tuning in a containerized environment. Myself, Vinayak, I have overall of 8 years of consulting experience, mostly working in like automobile insurance domain. Uh, yeah. So let's get started into the topic since the introduction is out of the way. Hope I'm audible to you all here. Okay. Is it better? Okay. Okay. So what is garbage collection? Anyone can try to like anyone can try to guess like what does garbage collection mean?
Recall the
Keep memory. Okay, you are okay. So here someone is saying that you're clearing the memory basically, right? Okay, so as it is stated, like basically in languages where you need to say malloc to allocate the object, and then later on say free to free the object. So that means you need to remember whatever you have allocated, and then you have to remember to free it as well, or else you will get dreams in the midnight that I forgot to free the memory somewhere. But yeah, that's a nice feature that is coming from Java, where like it is managing the allocation and deallocation for you, so that you can mainly focus on your problem statement that you are trying to solve. But again, sometimes it's like a double-edged sword. So sometimes it's a benefit, sometimes it's a disadvantage, because the time that you spend tuning your application or tuning your GC might be, I mean, that has improved over the time. So that is how it does. So anyone can guess how Java does this process? Like maybe a simple guess. How does it do?
separate development runs
Okay.
and different algorithm markets like that. Taking of those algorithm and then accordingly reclaim all the algorithm. So it is a double thread that is running.
Okay, but how does it track those objects? Like I need to remove this object or that object.
If there is no pointer that is pointing that object,
Okay.
so it identify all those null objects. There is no reference pointing to that object. So it identify that this object is eligible for the garbage collector.
Okay, so basically, right. Okay. So the answer here is basically if there is no reference to the object, basically we can or the GC can claim it and clean that object. But let's say some other object which is there in the heap, which is pointing to some other object, and then there is that object again pointing to the same object. Basically, recursion is happening. So what will happen in that case? That will that be object kept in the memory as it is, or it will be cleaned up since no one is referring it?
Will be.
Okay, so there is something called GC root. So GC root is basically the areas which are accessible or outside of heap, like your main thread or your thread pool that you create, right? These are your GC roots. So whatever objects they are creating, these are the objects that JVM tracks. So if there is no reference from any of the GC root, that object becomes eligible for cleaning. So that is how like garbage collection is done. Okay. So this is a typical memory layout of your JVM. So this is not the same for like all the collections, but this is how it looks like. So first part is your young generation, and second part is your old generation. So in young generation, you have Eden region, then you have survivor space 0, survivor space 1. And old generation is basically when your objects get tenured throughout the GC cycles, it gets promoted to the older generation. Okay. And within Eden also, there is something called thread local allocation buffer. So each of the threads gets a dedicated space in Eden, which is roughly 200 to 300 KBs. So that space is there for each of the threads, so that there is no contention between threads to allocate data or allocate objects on the heap. Okay. and you might be wondering why there are like two small spaces, like why there is a survivor 0 or survivor 1 space. So basically, when the object gets created, let's say you are creating a you're creating the objects as you are executing through your execution program. So basically, that object will be created first in Eden, and that object will remain there for some time. But most of the objects are like very short-lived. You do something and you return something, and that object then later becomes eligible for cleaning. So that is the reason. I mean, okay, so that the objects are very short-lived. So sometimes the processing might take time, and then that short-lived object can remain there for some more time longer. So in that case, these survivor spaces are the spaces where that object can be kept for some time, so that it can be cleaned up from the young generation itself. Because once it goes to, let's say, old generation, the full GC cycles are kind of expensive in some of the GC algorithms. So that is the reason, like, you have survivor space 0, survivor space 1. So you give the chance to your young generation to clean up that object before it gets promoted to the old generation. So there is something called tenuring threshold. So it is a threshold during which the object has to survive the GC cycles. If that object has survived those many GC cycles, then it becomes eligible to go to old generation. So so that is how, I mean, these are like arranged through. Any questions on this one? Okay, assuming no questions. Okay, as someone said here, like, these are like principal operations that GC does, like marking the objects for cleanup. Like, let's say the object is no longer referenced from anywhere, so it becomes eligible for cleanup. Then sweeping is basically cleaning or claiming those memory spaces. Then scavenge is basically looking for spaces. Let's say you're trying to allocate some object, but like you don't have or you don't have a continuous space for that object. So basically, you'll be looking for across like wherever the space is. That's like a scavenge operation. And the last operation is a compact operation. So let's say one cycle has done the mark, another cycle has done the sweep. But as you can see in this picture, right? So there are, after the cleanup, there are spaces, but the spaces are like very much fragmented. So if the object comes that is like a half the size, then it won't fit in this particular place. So then the GC also needs to compact the memory, so that the object, I mean, you get a continuous space for objects that are larger. Okay. 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 Since the title of the talk was related to the containers, we'll talk about the issues that we face in container environments. So first issue that we face is like the application is running, but it's like in a zombie state. So for some reason the OM has happened, and the application is like running in a zombie state. I mean, it is not serving any requests, but it is still running. I mean, it is not dead, not alive. So it's like in between, which is zombie. Then there is a issue of OOM. Your application is running out of memory due to, I mean, whatever the reason is, like sudden spike of requests or whatever reason, OOM happens. Your application is out of memory; it cannot do anything. Then there is something else called container OOM. So let's say you are running your application in a containerized environment called Kubernetes. Let's say in that you get a facility of setting request and limits, right? So you set a limit, let's say of 1 GB, but your application you haven't set any limit of 1 GB. Let's say whatever application you're running, basically it goes beyond 1 GB as well. So that time your container orchestrator takes a decision to kill the container because it is exceeding the predefined limit of memory. So that's a container OM. In an ideal scenario, you shouldn't rely or I mean, you should have your limits defined for your own JVM rather than the container orchestrator coming and killing your application. So ideally, it should happen. The first OM should happen. Second OM should not happen in most of the cases, because basically that means your application is not tuned or doesn't know what your limits are. Okay, and yeah, unpredictable workload. So let's say sometimes your task takes or API request takes like a millisecond of time, and suddenly it takes like 2-3 seconds. The reason could be there is a GC algorithm which is running in the background, and that is taking all your processing time, and that is why like one sudden request will have a time. I mean, that will take more time. That can happen in one of the job processing as well, where your jobs are taking let's say 1 hour, but because the GC is intervening in that job, it might take like 1 hour, 1.5 hour or 2 hours. So that becomes an unpredictable workload. And I think the last example is for the latency, where your requests are taking suddenly more time because GC is running in the background, and that is affecting your application threads. Okay, we'll see some of the solutions to these commonly faced issues in the upcoming slides. Okay, so these are some of the prerequisites to the tuning. Let's say the first flag is like adding a first case is exiting out of memory. So this flag is basically XX is for like the JVM parameters for garbage collection and tuning. So here plus means it's a Boolean flag, so you are setting that flag to true. If you set that to minus, it will be just a negative flag. Okay, so once you set this flag, basically your JVM will get killed if there is a OM happens to that process. So or else the process will remain as is because there is no flag set. So the default behavior is not to kill the JVM anyway. So you can make sure that the JVM gets killed, and maybe it can restart and serve the request, because it will get stuck up in that zombie state, or it will not serve anything, right? So that's the reason to add this flag. Then second is print the flags. So the JVM has certain settings, right? So you want to see what are those settings that are getting picked up at the startup. So this flag will print all the flags that are used by JVM at the start. We'll see a demo as well, like how does that look like. Then third thing is GC logs, because most of the time you are not sure whether it's a GC issue or not. So to determine it's a GC issue, you should have logs with you, so that you can see that clearly there is a spike in let's say pause time of young collection or old collection. So I mean that way you'll be sure that there is a GC issue and I need to tune it. So that's the thing that's the reason we are setting up this GC logs. Then final thing is basically adding or making sure that the container has the tools to support the debugging. Like in this example, the JMap is a tool that will help you let's say take heap dump or see the histograms of the objects on the container or the JVM. Okay, this part is basically okay. So if you are publishing the metrics for your application, then most of the providers or like maybe I'll take an example of Micrometer that publishes metrics about your JVM as well. So there are metrics related to GC pod seconds, allocations, promotions. You can monitor this. Like you don't need to go inside your JVM for this, because these metrics get published and your Prometheus can record it. So it will be easier to look it from outside as well. I mean, you can set up alerts on that as well if your GC pods are going let's say beyond certain threshold. So yeah, so this is like a prerequisite where you are doing certain things to make sure or to ascertain that there is a problem with GC. Okay, I'll go to the next. Yeah, so we need to tune the GC settings only if you are seeing the long pauses and there are frequent full GCs happening.
Question. Previous slide.
Okay.
Those are the only parameters, or there are other parameters also that we can look for metrics?
I mean, these are the few ones that okay, so sorry, should I repeat the question? Okay, the question is, are these the only metrics that we should be looking for? No, there could be more, but these are the ones that will highlight the symptoms that we are looking for, basically the pause time and the allocation rate. But there are more metrics as well. Like you can watch out for those metrics. I mean, the more you look for the data, you will get more behavior of your system. So you can watch out for the other metrics as well. But yeah, this is for just ascertaining that there is a GC issue. So that is only highlighted here. Okay, should I move ahead? Okay, cool. Okay, so first reason is like long pauses. Second reason is your frequent full GC. So if you are using some of the older algorithms or maybe concurrent or parallel collectors, you are seeing full GCs happening. So full GCs are mostly also takes more. I mean, there are two problems. One problem is basically your GC taking more time, and because your GC is taking more time, it will affect your application threads. Second problem is your GC is running fast, but it is happening very frequently. That means it is pausing your application thread more frequently. So that will also affect your application performance. So like that is also one of the symptoms where you need to tune the GC in that case. And then another problem is like OEMs are happening very frequently. That means either you have given very less size to your GC, or the GC is not getting a chance to clean up the space.
It can also be that you have a memory leak somewhere.
Yes, memory leak can also lead to frequent OM. Let's say your application is creating some objects, but it is not releasing the references. That could lead to a memory leak, and that could like develop certain frequent OMs. In that case, you should be looking for tuning the GC as well as looking at the heap dumps to ascertain if there are like certain memory leaks or not. Okay. Okay. Yeah. So GC is trying. I mean, for the particular GC algorithm, there are these three optimization goals that are given. I mean, it will only. I mean, first two are the only ones that will affect your application. So it will try to complete one of them first. And if it completes that, then it will try to also give more priority or try to complete the second one as well. So let's say your so maybe I'll talk about application throughput first. So what is throughput here? Anyone? Okay, sorry. Then I mean, okay. So you're talking about your application throughput, correct? But I think here it is talking about the time you are getting for your application versus GC time. So that if your application is getting more time to process the data or process the request, that means the throughput is more for your application. Your application can process more essentially. So that is one target that you can instruct your GC to like consider for more throughput. So for more throughput, generally you increase your heap sizes so that your GC will happen less frequently because there is more memory available. So GC will happen at a like more interval. So that means your application will get more time to do some stuff. But that will also increase your full GC cycle time because your memory is huge. I mean the full GC will take more time. So it's always a trade-off. So you need to watch out if you are latency sensitive or you want throughput. So that's like one of the goals that you need to decide for your application tuning. The second goal is basically latency. I mean, what is the latency that you can tolerate if GC pauses your application thread for some time? So that's your latency goal. And the third one is the memory footprint. Let's say you have more CPU, but you want to restrict your memory to, let's say, a very small heap. That means you can give more threads to your garbage collector to execute so that it will free up the memory faster. That means even with a smaller heap, you can basically you'll be able to service the request. So that's a memory footprint goal. I think there is a question. Okay. Okay, so these are the basic three goals that we look for. Yeah. Then okay, so there is something called JVM Ergonomics. So depending on where the JVM is running, it auto tunes itself. So let's say I'm running on my machine, it will basically have different parameters as compared to, let's say I'm running in a container. So that is where this ergonomics comes into picture, where depending on the environment, it auto tunes itself. So we'll see the one of the demo. It tries to maximize those one of the two goals, pause time and the throughput. That those two goals that we saw earlier. And let's say you are trying to debug some issue, right? And your local environment versus the target environment could be a lot different, because based on your environment, the algorithms that get picked up, right, might be different. So that is the reason, like, you need to be aware of your ergonomics. So how will you know about what are the flags that are getting picked up? So that the print flags final, the setting that we saw here. So this is the setting that will help us. So maybe we'll see some demo now for the ergonomics. So before we go into ergonomics, I will set up a context maybe regarding the application that I'm using. So it's a simple parking lot application. It is not doing much as of now. Okay, let me know if this is visible. I mean, I'll not be spending much time here, but like, this is a simple application, which is okay. Is it visible on the other offices?
Yes, it is.
Yes, it is.
Okay, it's a simple application. Okay, good. Thank you. So it's a simple application which is like generating a garbage for us to see how the GC gets picked up in this application. There are some other functionality as well, but we'll not be touching that at this point. So only this main application will be tested. So I'm using Java 17 here, like a simple Java 17 application, which is a Spring Boot application. And I have a okay. How do I exit? Okay, so I mean, yeah, this is a simple application setup. Now we'll go to yeah. So I have built the image. Okay. Okay, I've built the. Okay, is it readable here?
Yes.
Okay, so the image is like a parking lot image, and it is exposing certain ports, 8080 for the application port, and then these are the two JMX port that we will be connecting to. There are certain things here, like we have mounted volumes, like we have mounted a dumps volume. This is for getting the heap dumps. Then there's some flag here which is on failure restart. That means every time there is a failure, it will just restart it. But maybe I will comment this one for now. And we don't need volumes as well. And okay, so I will remove the CPUs as well, because let's say how does the ergonomics looks when there is no limit or nothing, right? So I will try to provide that. So yeah, this generate garbage flag basically decides when to generate the garbage. So to start with, maybe I'll set it to false because we first want to look at the ergonomics parameters. In this environment, I'm setting the Java tool option to expose the JMX data, so that we'll be able to connect with the visual VM and look at what is happening. Okay, so this is my Docker Compose file. Like I'm just spawning a one particular container with certain parameters. This is my setup. Any questions here? No. Okay.
Just for the clarification, the generate garbage and delay flags are the environment variables of your application.
Yes. So these are the two applications specific variables, the code that I've added for the demo purpose. Okay, I will clear this up. So basically, I'll just bring the whatever changes we did to the container, right? So the container should have them. So the container has started, which is this Sahaj parking lot. It is exposing certain things. We'll look at the logs of the container, which is this GC app 1. Okay, so it has picked up the Java tool option, but it hasn't recorded anything. It's like a simple Spring startup log, right? But I think we wanted to add the Java prints final flag. So let's add that flag here. I will pick that flag from here. and restart the. So I'm just restarting with that flag, and now if you see the logs, there will be some difference. Okay. 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 So basically, this looks aligned, but I think I'm using on a. So usually this prints in a formatted fashion, but because I have zoomed in too much, it is not showing that. But the thing that you should be looking out for is the ergonomic ergo. Yeah, so this flag. So here you can see the use G1 GC flag is set to true because of ergonomics. That means based on the current environment, which doesn't have any limits, it has picked up G1 GC. G1 GC is one of the Java garbage collector. So it has picked up that G1 GC algorithm based on the environment. Then there is this compressed ops. So again, it is ergonomic. So these are the things that will get applied dynamically based upon your environment. So let's say you're trying to debug your GC related issues, right? So you need to know what things or what parameters are applied based on your environment. So that is the reason you need to print this at the startup. So this log gets printed at the startup so that you can see what are those parameters. This just prints one, so not doesn't hurt a lot. But like it prints all of the parameters that affects your GC or your performance of your GC. Any questions here? No. Okay. Fine. Okay. So one more thing that it applies is the max heap, or maybe I'll just search for heap. Okay, so let me. Okay, so here it is saying soft max heap size is this. That means because I have not provided any max heap for the application, by default it is picking it from the environment, which is 1/4 of your total memory given. So no, we haven't given any. Okay, so limit is your environment, right? You're saying that my pod or container will have a limit of 4 GB. So your application is looking at the container saying that, okay, I have 4 GB memory available, but by default, because there is no XMS or XMX, I will just start with, let's say, 1 GB as my limit, 1/4. 1/4 as max limit, and 1/64 is the initial size. So that we can look at here.
Significance of 4 GB. If you don't specify anything,
okay, if you don't specify any limit, I guess whatever your let's say Docker process has as a memory. So I'm using Colima here. Colima is like Linux in Mac. So whatever limit I have given to that Colima process, that will be applied here.
One thing.
Yeah.
Here we are using 17.
Yes, Java 17. Yes.
But this behavior is not there in the older versions of Java, right? JVM.
I mean, yes, it is there in the older version as well. So in earlier releases of JDK 8, right, that is where the issue was, where they were not respecting the limits in the containers. They were getting the limits from the on the process that is running outside of container itself. So,
Can you elaborate that?
sorry?
Can you elaborate that part?
I mean, earlier it was not. I mean, it was not respecting those limits of container. But later version of JDK 8, they have made that fix, and it also respects the container limits. So it respects what container offers in a particular setting.
I didn't understand.
In earlier versions of JDK, so let's say you are running a process on a particular node which has let's say 32 GB of RAM, and but your container restriction is says that you can use only 1 GB of RAM. In some versions of JDK, earlier versions of JDK 8, it used to take the 32 GB limit directly instead of the limit of 1 GB of container. It used to take the 32 GB limit. So that is fixed in the later releases of that JDK.
1/4 of that 32.
1/4 of 32 GB. Yes. Now, if you have a limit of 1 GB and you don't have specified anything, so it will take 1/4 of 1 GB, which is 250 MB. Okay, so
Is it also possible just print out the flags that we are interested in? I mean, that prints out a lot of flags, right?
yes,
Because it just prints out whatever JVM has configured. Correct.
yes.
So is it also possible that we can print out the flags, let's say, what GC is being used, that only that flag? And is there a configuration like that?
I mean, by default, it just prints all of the flags. So there is no control because all the flags are mixed up. So you need to, I mean, you can do a filter or grep based on that. But I mean, JVM doesn't provide. Okay, so as I mentioned earlier, I'm exposing this on a JMX so that we'll be able to look at it visually using this visual VM tool. So this is again running on my local and I'm just pointing it to the process and it shows the overview, what flag we are passing, the argument, system properties, everything is shown here for debugging. In the monitor, you can see how much is your CPU usage, heap usage. Like at the start, it is only taking the 1/64th of memory. It seems to be increasing, but ideally it shouldn't. But okay, I mean, it is not crashing. Whenever we are enabling that garbage generation, right, it will crash very fast. Okay, so I mean, basically, we are able to visualize the VM here. You can see the request and the limit of that JVM. Now let's go back and add the generate garbage flag to true and let it generate some garbage. I'm again just applying the compose up. It will apply these things. So as you can see, it is just printing this garbage generation completed log. And we can go back to visual VM and see that the garbage is getting added up. So the heap is going up and up and up. Now we have given a limit of 4 GB, right? So it will hit a threshold of 1 GB and then OM will happen. And yeah, let's wait for that. Okay. So now it has reached, I mean, the limit has reached there. The usage is also catching up. Okay, so this is the one of the scenario that we discussed earlier, the zombie state. Now the OM has happened, but the container is still running. About a minute ago, it is still running. But if you go and check the logs of this container, right, it will say out of memory. So here this application basically zombie. Because it has gone out of memory, it will not process anything. It will not accept any request, but the process is still running. So how do we fix this now?
What are the other reasons the application might go on zombie?
I think this is one of the reasons that we observe it very frequently. Like if you don't add the exit on out of memory, right, it will stay there as is.
So usually kubernetes will detect like this kind of behavior that the pod is not responding. So maybe it will terminate this pod and it will try to create a new pod in this particular scenario. Is that correct?
Yes. Okay. So the question is, will the Kubernetes system will try to detect this scenario and remove this pod? Yes, it's possible. If you have added readiness and liveness probes, those will detect that the container is unhealthy. I need to remove that container. But if you're missing those readiness and liveness probes, right, then there is no way to recover from this unless someone is coming and telling you that your application is not working. Right? Okay, so how do we fix this?
Hey, sorry, I have one question. We
Yeah.
specified the memory limit as 4 GB, right, in the Docker Compose.
No,
How
the
come
limit,
it's crashing at 1?
yeah, that's what we discussed, right? So the limit 4 is for container, but we haven't specified any limit for your JVM application. Yeah, I mean, you haven't specified any XMS or XMS flag or any max RAM percentage or anything, right? So that is the reason it is picking up a default value, which is 1/4 of your total memory. So total memory available to container is 4 GB, and out of that, it is picking up 1 GB as a limit.
All right. Thank you.
Okay. Okay. Okay.
Vinayak, just wanted to
Yeah.
check.
Yeah.
So here we killed the application, isn't it? So the application went out of memory. So is it not possible to kill the container itself? Because if the application is not running, then what is the point of running the container? Unless there are multiple applications running within the container.
Okay, so the question here is, I mean, can we kill the container itself because the application is not running and it is not serving anything? So usually, if you add this flag of exit on out of memory, right? So that will kill your JVM, and if the JVM is killed, then your container will also get killed as effect of that. So it will happen once the JVM gets killed. PD.
Okay, that's a part of the solution you are saying, right? It's
Yes.
a part of the solution.
Yes.
Okay. Mhm.
So we'll add this flag of exit on out of memory,
Mhm.
right? So this will, let's say, so same thing will run again.
No, but this flag has been applied on the JVM, but it reflects on the container too. And that is where when you mentioned that now JVM works closely with containers now. So with these flags, so it has some kind of an handshake mechanism with the Docker container. Wherein as soon as it goes out of memory, it's an indication for container as well to kill itself.
Oh, it's a simple parent process and child process, right? So your container is your parent process and child is your JVM. If the JVM is getting killed, that means the parent has nothing to wait for. So it will also kill itself.
Right, right. No, but again, this setting is at JVM level, at the child process level. Not at the
Yes,
parent
yes.
level.
Because container doesn't know if the JVM has exited or not, or it doesn't know if the JVM is healthy or not. As someone said here, like we can add those readiness and liveness probes so that the container will also know that the process is healthy or not. Then container can take a decision to kill it or not.
So this support is not there on Java 8. So in later versions, this support was added.
This flag is, I think, there since start. I mean, as far as I can remember, it is there in JDK 8 as well. So only thing was the respecting the container limits that was not there, but they have added that later on.
Okay, okay, cool.
Okay, I will go and apply this. So it will just recreate the container. So now it will say this. So here I will go back again in here. Now you can see it is again started to pick up the things. Okay, maybe one thing we could do is to reduce the time interval, but that will be too less. But okay, let it happen. So one thing that you'll notice that the container will now recover itself because the process gets killed. It will start and it will start to populate the garbage again. Just let's wait for a couple of seconds. I guess it will happen.
So until that happens, I have a question. So
Yeah.
now, like we mentioned that even Kubernetes or orchestrator frameworks, right, provide readiness, liveliness mechanism. So even when we have those, should we set this flag to true?
You can set this flag. Yes, I mean it's like having a setting in both. Let's say for some reason, I mean it's good to have both. In my opinion.
Maybe the JVM setting could be more instant because the readiness probe will happen like every few minutes or seconds.
Yeah.
It will terminate as soon as it happens.
So because the readiness and liveness probe will be waiting for, let's say, I mean it will do it 3 or 4 times with certain timeout. So it will be longer. But here it will be instant. The moment the OM happens, it will get out of memory and it will start again. Okay, let's see if that container is there. Okay, did it not kill?
One point here.
Yeah.
So having this flag, let's say there is an issue with your application because of which it is consuming more memory, then it will go on limp, right? Your container will die instantaneously as soon as your application goes to it. So then we have to go and basically respond such links also.
Yeah.
Can that be an indication of how we can get that?
Yes, I mean that is one of the indications, right? So basically, we look for the symptom which is frequent OMs. So if your application is starting quite frequently, then it's a symptom to go and look at your GC and memory and heap dumps for memory leak and stuff. Okay, so if it remains stuck, then your application is stuck. So your application is not responding to requests. So instead of that, at least it is restarting and then starting from the scratch. So that's one good thing about adding this flag. Okay, so the container has been killed, but because we removed that restart setting, it is just there in the exited mode. It will not do anything. But let me go and add this restart on failure because we want to like see that happen. Like it will start again and again, right? Sorry. Yes. Change the delay. I'll make it half. Okay, it has started. It's asking me to reload. Okay, let it happen in the background. We'll just go look at the slides and come back here because we again need to add few more parameters. So let it happen in the background. It will not affect anything. Okay, we were ergonomics we looked at. Then second part is like collecting the heap dumps. So let's say the frequent OM is happening and the application is going restarting itself and going ahead. And since the containers are ephemeral, you lose the data the moment the container restarts, right? So in that case, you lose logs and dumps and everything in that case. So how do we make sure that the logs or the heap dumps are preserved? Any guesses? I mean, one thing is like you can just mount the volume. In this case, example also, I've just mounted a volume which will collect the heap dump. And you can also log, let's say, DC related logs into that volume. Okay, so in Kubernetes, there is something special called empty volumes. These empty volumes are directly mounted from your, I mean, the disk which is available on the node where the container is running, right? So you can create an empty volume just for the heap dump sake. So whenever, let's say, heap dump happens, your application will create a heap dump. It will add it to that volume. And once there is some data on that volume, you can also generate the alerts. Let's say the heap dump is created, then you can generate the alert so that someone can go and look like why the heap dump happened in the first place. Right. So then it's like you know that heap dump is happening because of OM. So you go and look at the cause of that heap dump. Maybe the size is not enough. Maybe the GC is not happening soon. So any one of the could be the reason. Okay. Sorry. Yes, you can add a persistent volume, but again, it's like there will be a cost, right? Because some cloud provider will be providing those volumes. But here it's like a transient thing where you can quickly go and copy that heap dump to your local end for analysis.
So it will be there on the server. I mean, volume you are getting. So it will be there. Maybe the pod get terminated, but the heap dump will be there in that particular.
Yes. I mean, okay, so container will restart automatically because the process is killed and pod will restart that container. But the volume is attached to the pod. So unless you go and delete the pod, that volume will remain there. So it's like an ephemeral volume attached to the pod. So the containers can restart, but the data will still be there. Make sense? Okay. Yeah, let's add these two flags and let's see how we can retrieve that heap dump. In my case, in the demo's case, the heap dump is mounted as a volume on a Kubernetes, but it's a local volume. So I will be just able to go and look at it. But you can copy things using Docker CP or kubectl CP. Sometimes the kubectl CP gives the issue. Then the best case will be just going to the node where that container is running and then copying from there. If it is not possible, maybe you can add a process which will sync those heap dumps to, let's say, a particular S3 bucket. If it is, I mean, if you don't have access to your node to copy that data, you can sync it to, let's say, S3 bucket and copy it from there. Okay, let's go and look at that, how it generates the heap dump. But before that, okay, you can see here, there are like, it is going up and down, because every time it is reaching a limit, it is getting restarted and then starting to generate garbage again. It's like a cyclic process here. Okay, so let's add these heap dump flags to this. The flag is heap dump on out of memory, and you need to specify where that flag needs to go. Okay, and also we need to make sure that we have a dump volume. Yeah, okay, so yeah, we just make sure that we have a dump volume as well, that will dump this information here. I will start it again. It will recreate the container.
So there are two ways of doing it, like one while running application.
Yes, so
Keep on adding whatever is the status.
yes, I mean, first we'll take a look at this, and then maybe we'll stop the garbage generation, and then we can look at how you can take a, let's say, on demand basis, you want to take a heap dump, that will also take. Okay, it has started 4 seconds ago, and let's verify the local directory. Okay, so it has already generated one heap dump because the interval is less. It is generating it already. So heap dump is already there on my local. So how do I visualize it? So there is something called Eclipse MAT, Eclipse Memory Analyzer tool. So this MAT tool basically can help you analyze those heap dumps. So basically you can just say, I want to open a heap dump which is there in this dumps directory, and it will open. So this MAT tool can give a lot of insights as well, like where are the leak suspects. You can ask for a leak suspect report or component report, or let's say any run reports. So I mean, this tool also is like in itself is a vast to look at. We'll try to just look at the surface, like what capability it provides. You can maybe ask for a leak suspect report, and it will give you a leak suspect saying that there is a leak which is happening in main thread, which is like contributing like 96% of the heap, and it can also provide a stack trace, like where that is generating. So it will provide you the stack trace. Okay, it is happening while allocating the memory, and it is generated by. Okay, maybe I've clicked on.
There was a parking lot application, line number 23. Below that, in blue.
Yeah, correct. This is this one. Okay, this is the one. Okay, so this is pointing you to the place where the garbage is getting generated, right? So basically, this can provide you that an insight. And you can also look at like histograms here. The histogram can be looked at by different tool as well. So there are different tools available to do all of this. So this is one of the tool. So it can show you histogram as well, like what object is there, what is the count, what is the size occupied by that object. So here most of them are strings because I'm generating a random string. So that is a string here. Okay, we'll go to the case where we want to acquire a heap dump where the process is running, and we just want to look at what is there in that heap dump. Okay, I'll set this to false so that we want to take the heap dump ourselves. Okay, sorry, any questions from the offices? Okay, okay, assuming no questions, we'll go further. Okay, the container has started. Maybe I'll just exec into this container using a bash. Here I can, so there is this tool called JMap. So this can let you, this can help you take the heap dump in the running process. So this is one option where you are saying, I want a dump of all of the heap, and I'm just giving a file where you want to dump it, which is in the /dumps and manual, and format is binary, and I'm just providing a process ID. because this is a running in container, the process ID is 1. So okay, I think I have missed something. Something is, this is just B for binary. So it is dumped into this particular folder. So if I come out of container and just do /dumps, so it has generated this manual HPAF file. Yeah, and then similarly, you can go into MAT, open that file and look at it respectively. JMap also provides heat map. JMap also provides a capability to look at histograms. So, for example, this, right? Okay, it is taking me there. Okay, I'll just copy this part. So you can see the live histogram and just provide the process ID. So it will print the histogram in the console itself. So, I mean, looking at the heat dump is not the only way to look at the histogram. You can also look at it while connecting to the process. Okay. Any questions till now? Okay.
One question.
Yeah.
Is JMap something that you had to install separately, or is it like bundled with Java?
Okay, JMap usually comes with a JDK. It doesn't come with a JRE. So that is the reason like you need to have it installed separately. There are tools like JSTAD, JMap. So these are the tools that come with JDK.
Okay.
Okay. Okay, we have looked at collecting the heat dump part. So before we go further, just let's, I think I forgot to look at one case where, okay, so what if we set this CPU limit to 1? Any guesses what will happen? Yeah, I mean, we are giving just one core. What, any guesses what can happen? Okay.
The process will not get enough threads when GC will run.
Okay, so the ergonomics will kick in again here. Let's look at that. So if I look at the logs, so earlier you saw that use G1 GC was correct, right? I mean, was set, but now it's false. The reason being, you have given a less process and it has picked up use serial GC. Serial GC is one more garbage collection algorithm, and because you have provided less CPU, right? It is basically picking that as an ergonomic. So that is the reason like you need to be aware like what you are passing to your containers. Let's say you have set the limit, not thinking about like what your GC will pick up, right? Because JVM will think that I have only one processor, and within that one processor, application also has to perform as well as GC has to perform. Then it thinks that maybe it's better that I use serial. But in this case, even if you have like a 2 or 3 GB of memory given to your container, but your GC algorithm is still serial. So it will take more time when the full GC happens. Okay, I mean, we'll go into specifics of the algorithms after this. So we saw the collecting heat dumps. Then the next point is basically monitoring your application. You can you need to enable your remote connection using JMX and then just connect with any of the tools. I use Visual EM, but JConsole and JF are also similar tools. They also have like a little bit of different functionality, but they also let you monitor with the similar capability here. Okay, we saw this. Okay, so next part is, I mean, this part is maybe agnostic of containers, but this is still applicable to containers. So next part is basically choosing a right garbage collector for your application workloads. Okay, first collector is a serial collector. As per name, it's like a single threaded serial collector. It collects young generations with a minor GC, old generation with a full GC. But it is only suitable for where like heap is very less, 100 to 300 MB. That means it will need time between like milliseconds to clean up that area. But if you provide more area, it will take more time, which will affect your application threads. So that is the reason. People thought that this algorithm is useless, and then containers came in, and in containers, most of the time you provide very less resources, and this guy still makes sense. Okay, cool. The next collector is parallel collector, or we call it as a throughput collector. Why throughput? Because it collects the or it does the collection parallelly using multiple threads, and it completes in faster compared to serial, and it gives that time back to application so that your application can perform. So that is why it's called throughput collector. Again, here like you can do a behavior based tuning okay, so in parallel collector also, that like you can assume for one of the behavior, right? Either performance, which is throughput, or latency. So if you specify for latency, you need to adjust the value for max GC pause millis. By default, there was no value earlier, but now I think there is a value of 200 milliseconds. So if you don't provide this goal, I think for parallel collector at least, it will try to optimize for throughput rather than latency. So by default, parallel is for throughput because it optimizes for throughput by default. And the next part is throughput. So throughput is basically specified in terms of time that we give back to application, right? So here the time is specified using this GC time ratio parameter. The parameter is specified. I mean, the formula for that value computation is like this. So whatever you provide, right, it will compute the time using this formula. So let's say you provide 12 as a value here, which will be around 1 upon 1 by 13, which comes close to 8%. So that means application will get 92% of the time, GC will get 8% of the time. So that is how the split of the time is specified here. Earlier, this value was just 99. 99 meaning if you do 99, then it will come as 1 upon 100, which will be just 1% of the time. JDK 11, if you are running a parallel collector in default setting, it will allow only 1% of the time for GC to happen. But yeah, these settings have been like tuned to normal now because in JDK 1% of the time to GC. So your GC will run only 1% of the time. So if it is exceeding this limit, it will not let GC run. So, I mean, you need to also watchful, like if the default is affecting your application. If your GC is not running, that means this could be one of the parameters that is limiting your GC to run because you are saying that I want only 1% of the time it to run. Okay. Again, the next parameter is footprint. Footprint, again, you control it using your XMX flag. So you set that flag and it will be controlled. Most of the times, if you want to improve your throughput, adding heap is one solution. Like if you have more heap, the garbage collection will take time, or at least your allocation will happen faster, and your GC will take less time, or it will take more time to run GC in the first place because you have more memory. And then there are like additional tunings which specifies min heap ratio, max heap ratio, and then the adaptive sizing. So it can also adaptively resize your young generation, old generation, because if the promotion is happening too faster, then your new generation needs to be a little bit larger. So it can auto tune itself adaptively looking at your past GC cycles. Okay, yeah.
Can you explain the latency? Still internal latency.
Okay, so your application is, let's say, latency sensitive, but you are running a parallel GC in the application.
Yeah, what do you mean by latency?
Okay, so latency is the time which you can tolerate. Let's say you are giving max GC pause as 200 milliseconds. That means you can tolerate 200 millisecond GC time, which can affect your application. So if that time, let's say 500, then that if your application is very latency sensitive, it will get affected. So you need to define what you are okay with. And again, this parameter also determines in some cases your heap size. If you're not providing your heap size, JVM will take the heap size only the heap size which can satisfy this time criteria, because you are saying I need to satisfy this criteria. Let's say you say 50 milliseconds, then it will have the heap size which is only that 50 milliseconds can manage.
So that is the maximum this size.
Maximum heap size, yes, it will restrict that as well, because the goal is latency, right?
Even though we have text.
I think XMS overrides that, but most of, if you are not provided XMS, it will take this, because you're okay. So if you are specifying XMS as well as this, that means you are specifying your two goals. So that means that the JVM will try to honor these two goals at the same time. But it will struggle if you have large memory and less time. That the first goal will obviously get affected because of large memory.
So latency makes sense to the applications which are like continuously running. They have to. Oh, they're getting.
See, your GC pause can come at any point in time.
Correct.
So if that pause affects your request or processing, then the application developer need to decide what pause is like I can handle or it's tolerable to me. And then you decide either this collector or that collector.
But like, so let's say that you gave like 200 milliseconds as a GC pause. If the GC is running, would it like leave it in the middle? Like what would happen to it?
No, it will try to complete or it will just complete that much.
It can in 200.
Yes, yes. It will.
We are not giving enough time.
Yes.
To clean up the memory.
It will keep on. Yes. It's not interrupt, but okay, it will limit the heap size itself. So if you. Yes, it can. Yes.
There might be another object, but that is still like.
It will be completed in the next cycle, but yeah, again, that will increase your time for the next cycle.
So on the throughput, you said like you did some calculation and you said 1% like entire application time it would take for the scale. So does that mean that out of 100 minutes, let's say my application is running for 100 minutes, so out of 100 minutes, 1 minute it will spend for doing the
GC. Yes, that's correct.
max.
At max. If it is exceeding that, then it will not allow GC to run, because you want the time for your application rather than the GC. And here there is one more thing with parallel connector. If your application is doing GC 98% of the time and it is not able to reclaim any space back, it will just say, boss, I couldn't get any memory. I'll just kill myself, because you're not doing anything with 2% of with application, right? So it will just kill itself, saying OM, I can't process further. I mean, okay, so it's similar to, let's say, it is doing too much GC, like 90% of the time it is doing GC, but still it is not able to get memory back. That means it can't process or it can't do much here. And then it gives up saying that I can't process.
But like it won't go to 90% if you're defining throughput, right?
Yes. Again, these are like defaults are there, but you can override them as well. Okay. Okay, next is the garbage first G1 GC collector. So G1 is like garbage first. So here it is still generational. That means it has young generation, old generation. But the only difference is it doesn't look like a similar single memory. It has regions. So these are the regions which are like, let's say the one highlighted with S is for survivor space. Some of them are highlighted with red. These are for like Eden generation. Eden is basically initial part of your young generation, and then this H is for humongous objects, and the rest is, I think, blue one is for your old generation. So these regions are like 1 MB, like minimum region size is 1 MB. So if your heap is, let's say, 2 GB, there will be like 2048 regions total. And basically the G1 GC goes through this cycle where it starts with marking, then it does a cleanup. Cleanup actually doesn't do any cleanup here. It just identifies the region, And in this young only phase, it only clears the young generation. In the second space reclamation section, it reclaims some regions at a time. So if you have, let's say, 10, 20 regions for cleanup, it will complete, let's say, 5, 5, 5, 5, and then it will go to young only section again. So it doesn't do everything at once. It does only few regions at once. But during the young generation, the threads are stopped. The threads are paused for cleanup. So it is still pausing the threads here. Okay, similar to earlier algorithm, it also accepts these. Yeah, it is still okay. Okay, parallel because there are multiple threads. G1 is called concurrent because it runs concurrently with application threads. So in this half, it doesn't stop application thread. It stops the application thread only in this half.
That's called concurrent.
Yes, it runs concurrently with your application threads. Okay. Yeah. So again, here, if you set the max pause millis to higher value, you'll get a higher throughput. But your GC pause time will go high. And latency, again, if you set it to a lower value, your application will perform to the latency. I mean, it will serve response faster, or it will not have the that it will not exceed that limit. So this is the goal that you can specify. You can also adjust the concurrent threads and like the time it can run. But again, if you're using G1 GC, you can go further and look at this. This still has a like overhead in terms of like it pauses the application threads, and it has a space reclamation overhead. Yeah, and it is meant for heaps larger than 10 GB. Like if you have multiple GBs of heaps, then it makes sense to use G1 GC, because even in Java 17, right, the ergonomics choose G1 GC as a default algorithm based on your environment.
When you said the higher value is in context with the value that is being set for.
Yes, this max GC pause time, if you set it to a higher value, you'll get throughput. If you set it to a lower value, you get latency. So these are the two goals that you optimize for, right? And yeah, and this is meant for larger because solely because these regions, right? Because it manages these regions, space reclamation is easy, and it is performant compared to parallel, but not to the ZGC, which we are going to look at in some time. Okay.
So one question.
Yeah, sorry, go on.
It works, or rather, garbage collection is done in parallel, or rather, while the application is running, the garbage collection happens, or multiple threads collect garbage at the same time. So what happens in parallel? Running of application plus garbage collection, or garbage collection happens in parallel? No, G1 GC.
Okay, in G1 GC also there are multiple threads. It's not like it's running only on a single thread. But the pause is not happening, and that is the reason it is a bit different. In this half, right, the pause doesn't happen. Only this part where it pauses the application threads. And I mean, there are multiple threads. This is like a phase it goes through. So in this phase, it will only clean young generation, pausing the application thread. In this phase, it only cleans the old generation without pausing the application.
Okay, but generally, in general, when it comes to garbage collection in JVM, for old generation cleanup, the pause time is higher, right? But like
yeah, but it's not locking the entire region, all the old generation, right? It is locking only some of the regions. So it's not pausing all the threads here.
Okay.
Okay.
Got it.
Okay. The next one is ZGC. It's a non-generational. That means there is no old or young generation separation here. It is managing regions like this, but there is no separation between the regions. Okay. So it is also concurrent. I mean, you can specify the concurrent number of threads. Usually, you should not specify more threads than you have CPUs available, because it will again affect your application. If you have more threads running GC than your application, then it again affects application. Here, GC pause doesn't increase with the size of the heap because they do something special called like adding a barrier. So it basically adds a barrier when the thread try to access the object. So let's say you are trying to move the objects underneath during the cycles, and the thread also tries to access the object because this thread is not paused. It will still try to access the object. Then in the object reference itself, they have added a barrier which will stop this thread or pause this thread, only that thread, till that movement completes, and that movement usually happens within milliseconds. So only if that thread is trying to access the data, then only it gets blocked on the barrier. So here they are not stopping all the threads, and that is a main selling point of ZGC, where it doesn't stop the application thread unless you try to access it. It's yeah.
Does it mean there is no top of the word activity in ZGC?
It is there, but okay. So the question is, there is no stop the world activity in ZGC. It is there with that barrier, right? It is still there, but only for that thread. So it is not stopping the world per se. It is stopping one thread maybe, or the threads or the threads that are trying to access the data. Yes. Okay, and then this is intended for like low latency applications because it doesn't affect the latency doesn't increase here. And it also returns the unused memory back if you set this flag. Sorry, is there a question? Okay. Okay, so it was experimental in Java 11, but now it is available as a full production supported version at ZGC. It is available since in 17, the LTS release 17, it is available as a production version. Yes. Okay. So final collector is epsilon collector. As the name suggests, it doesn't do any garbage collection. It just allocates the memory but doesn't deallocate. So it is suitable for cases where like you have a short-lived process or job where you don't want to add the overhead of running garbage collection, because you know that this will complete in like very short time. Let's say running a test or running, let's say, some job which doesn't require your memory allocation or everything. I mean, memory allocation is needed, but cleanup is not needed because the job itself will kill in some time. So for this epsilon collector, it doesn't do cleanup, so it just does the allocation. The moment the heap size reaches its top right, it will the JVM gets killed there itself. So that's the epsilon collector. So it doesn't add up any latency due to GC running in the background. Okay. Cool. Okay. Final thing is heap sizing. So
Vinayak,
sorry.
Yeah, the epsilon collector, is there any advantage of using it over the other ones? Okay, so
It is suitable for only for like short running jobs. You cannot use it for your regular applications because your regular applications needs to reclaim the memory back, right?
But if you are using this, is there any advantage over the other ones?
Yes, clear. The GC will not be running in the background.
Okay.
So that means you get all the 100% of the time for your application threads.
Okay, got it. Okay, thank you.
Yeah.
It's a short-lived, like, for example, if I have a lambda,
Yes.
where I don't want to have because I know that this is a very short-lived.
Yes.
I can use this value.
Yes. If it is very short-lived application, you can use epsilon collector, where you don't do any collection. Thereby, like at the startup, JVM Ergonomics is doing some calculation, right? What heap size do I give? What algorithm I choose? All of that goes away because you are saying I don't want any garbage collection. Okay, next part is regarding heap sizing. Throwing more hardware at a problem is not a solution. So let's say you give more and more heap, doesn't mean your application will give the same benefit back of throughput to you. So there's law of diminishing returns. So this is a stock application from the book that I referred. So basically at the start, you see a very natural gain when you are increasing the memory. This is the heap size on the x-axis. TPS is transactions per second. for that stock application, it's like a transaction per second. So initially, when you increase the memory, it gave a good jump in the application throughput. It still gave that jump minimally, and at one point, adding more memory resulted in more overhead rather than more throughput. So that's one thing I want to like highlight. Like, don't just add up memory because the application is running out of it. Tune it. Okay, these are the two references that I referred, like actual Java documentation as well as one book called Java Performance. So these are the references. Yeah.
The first one completely.
The book itself is called Java Performance. It's a very detailed.
Is it the
I think it's the link. If you click on the, I mean, we'll share the slides on it. Yeah, if, I'm done with it. If there are questions, let me know. Yeah.
So you said so you allocate one CPU, right? I joined late, so that's one of my.
Yeah.
It will default to
Serial collector.
So usually in the apps we have less than one CPU. We allocate 224 or something. So how does it work?
If you're giving very less memory, right, then your ergonomics is coming into picture. Unless you're specifying that through some other means, let's say you're explicitly saying that I want to use parallel GC here, saying use parallel GC. So unless you're saying that, it will by default ergonomic will pick that.
So if I allocate one CPU, one core CPU, and if I does it explicitly say that to use a constructor, it will default to CPU.
Yeah, correct. I mean, okay. So the question here is, if I specify one CPU to the application, it by default it chooses serial collector, and it doesn't give you the choice because ergonomics is saying that because you have one CPU, you can't run parallel or throughput collector because these are more CPU intensive. So if you run them and you just have one CPU, that means you'll end up giving more time to GC rather than your application, and that is where Java is deciding that you should use serial collector. But that also limits your choice of the memory that you can give to your containers.
you can explicitly override this.
Yes, but you can override it. But again, with the limited resources, your application might perform poorly because you just have.
So if I select let's say 4 CPU, so will it going to take some other GC over there instead of serial?
Yes.
It's by default.
No, if you specify 4 CPU, right, then it will take G1 GC, for example, automatically. If it detects that there are resources available to run parallel collectors or G1 GC, it will pick up that.
Is there any way where I can find out all this GC parameter? I've not printed any startup, like I've not configured anything to print those things. I'm already running somewhere like this application in my pod.
Yes.
So is there a way I can get all these things?
Yes. So basically, okay. So maybe you just need to like supply this or run any Java application, and because this Java tool option is set in my container, right? I will be able to see JMap is also a Java application. Okay, so even if I haven't set any parameter in my application and I go inside the application here, and if I say JMap, it will print everything related to because that flag is there. You just need to provide that flag and run that tool. It will give you what is the ergonomic parameters that it is picking up. Make sense? Okay, any questions on the call? Cool. Okay, if there are no questions, thank you for attending it, taking the time out.
Thank you.
Thank you, folks.
Thank you.
Thank you.